Good morning, students. We are going to learn about virtual memory. Virtual memory is a concept used in large computer systems, that permit the user to construct programs as though a large memory space is available. It is a concept used in large computer systems to permit the user to construct large programs assuming that there is large amount of memory available. This virtual memory is used to give the programmers the illusion that they have a very large memory, even though the computer actually has a relatively small main memory. We know that in computers, the main memory space is always less. It is expensive. The main memory that is constructed using RAM and ROM chips and that performs faster than auxiliary memory is expensive. So very little space of main memory is maintained in computer systems. So even though the computer has a small main memory, this concept, virtual memory concept, give the programmers the impression, the illusion that they have a very large memory. How it is done? Here the programmer uses a virtual address. Virtual addresses, virtual means it is not real, right? The address used by the programmer is called virtual address. The CPU refers the computer memory using this virtual address. So this virtual, how the programmers are given the illusion that they have a very large memory. Number of bits used in this address, virtual address, is bigger than that of the actual space in main memory. So with that, the programmer get a feel of having a large amount of memory to work on larger programs. So what is address space? Address space is set of virtual addresses. Set of these virtual addresses form an address space. And physical address, you need to remember this. Virtual address is the address used by the programmer, which is not the real main memory address. And physical address is the address in main memory. This is the actual main memory address. It is also called as location. Physical address. This is the address in main memory. And this collection of this memory, set of these locations or the address in main memory are called memory space. And set of virtual addresses called address space. And set of this physical address, actual main memory address, is referred to as memory space. So memory space is set of locations or physical addresses. So the address space, that is a collection of set of virtual addresses. It is allowed to be larger than the memory space in computers with virtual memory. This diagram shows the virtual memory system, and the relationship between the address space and memory space. Here we have the address space. What is address space? It is set of virtual addresses. And it can be up to this address spaces. The size of this address space, the set of virtual addresses used by the programmers can be maximum up to the total number of words available in auxiliary memory. The maximum space allowed in address space is the size of the auxiliary memory. So here the auxiliary memory size is referred to as address space. And here we have the programs. Program 1 with data, the associated data, program data 1 and data 1 2, and program 2. The data associated with the program 2. And the size of this address is indicated here as n, and this is main memory. We have the main memory here at the right side, and it is denoted as m, the memory space. Means the physical location, physical address, the actual address, that is referred to as m here. And the virtual addresses, set of virtual addresses, form the address space that is referred to as n. And the total size available in address space is 1024K, means 1024 is 2 power 10, and K, it is 1024 times this. K is 1024 again, so that is 2 power 10. So the total address space is 2 power 20. So the number of bits needed to refer to each word in this memory in the address line is 20. Okay, the number of bits is 20. But main memory space, okay, actual physical locations available in the main memory, physical addresses, okay, set of physical addresses is memory space. And the size of this is 32K, 2 power 15. So the address bits needed to refer to these, what's in this memory are 15 bits. Okay, 15 bits are used. So now whenever a particular program is needed, how the execution is done, because CPU can directly access main memory only. It cannot access the auxiliary memory. So any program that is to be executed need to be brought to main memory. So here if program 1 is being executed, program 1 is transferred to main memory and the corresponding data, what is required for that execution. Okay, it is data 1 that is brought to main memory. Okay, and once this execution is over, the program 1 and data 1 is brought back to, transferred back to auxiliary memory. And for the next set of programs and the data, okay, related data are brought to main memory. And here the main thing is virtual address that is generated by the program. Here in this case, that is 20 bits, correct? 20-bit address. And here in memory space, we have the address lines will have 50 bits to refer to this word in memory. We need to map this address, the virtual address, okay, of 20 bits to the physical address of 15 bits. Okay, we need a mapping mechanism. Mapping is converting this virtual address. Okay, in this case, it is 20 bits. So converting the virtual address to the corresponding physical address to refer to the data in data or instruction in main memory. Okay, so how this mapping is done? A mapping table is maintained. Okay, for mapping the virtual address or to convert the virtual address to the corresponding physical address, okay, the main memory address, a table is maintained. Okay, that is called mapping table. It is a table, okay, that is needed to map the virtual address to physical address. Here, this is a mapping table, okay, memory mapping table. And initially the virtual address, we have the virtual address register. And in the in this example, the size of the memory is 1024K, so 2 power 20 bit. So the virtual address will have 20 bits. And the mapping table is used to convert this address into how many bits are needed to address the main memory? 15 bits. So to convert this 20 bits to 15 bits, we need a mapping table. Okay, so this mapping table is used to map this virtual address to physical address. Okay, we have here is a physical address. This is a virtual address and we have here the physical address. So to convert this virtual address to physical address, we have this mapping table. Okay, this converts it and stores it in memory table buffer register, and that is used as used here to generate the physical address that is of 15 bits. And this address is used to refer to the particular word in main memory. And once the content is located, that is transferred to main memory buffer register, okay, to be transferred to CPU. In the virtual memory system, this address generated by the CPU is virtual address. So it is in this case, it is 20 bits. So this need to be now converted to the actual physical address, that is main memory address of 15 bits. So for that, we have the mapping table. Okay, this converts the virtual address to physical address. And this address, physical address, is used to locate the corresponding required content in memory. That is stored temporarily in this buffer register and then later transferred to CPU for processing. So to understand this mapping, let's take this example. Here we have the address space. The size of it is 8K. Okay, so how many address bits are needed? 13. It is 2 power 8. K is 2 power 13. 8 is 2 power 3 and K is 2 power 10. So it is 2 power 13. 13 bits are needed to address these locations in the address space. Virtual address will have 13 bits. And we have the main memory here. This is the main memory and this is the auxiliary memory. So in main memory, the main memory space, right? This is the memory space, set of physical addresses. The size of this is 4K. Okay, it is 2 power 2 plus into 2 power 10, it is 12. So 12 bits are needed here to refer to these locations in main memory. And here in this address space, the virtual addresses, so total size of 8K is divided into equal size pages. Auxiliary memory is divided into smaller units. Those smaller units are called pages. So we have, as we have 8K memory here, it is divided into 8 pages. Okay, from 0 to, they are numbered from page 0 to page 7. What would be the size of each page here? Each page is 1K. Okay, total size is 8K. It is divided into 8 pages. Okay, so this division of the address space, okay, total address space into different smaller groups are called pages. Okay, so we have 8 pages here, numbered from 0 to 7, each having 1K space. The memory space is 1K. Okay, this we are doing to map page, okay, that is an auxiliary memory that can be transferred anytime for processing to main memory, and the mapping can be done, mapping between the content, okay, that is when that is moved to main memory can be done. Okay, so here in main memory, if you see, this is 4K, the size, total size here is 4K, so it is divided into 4 blocks. Here the division of this memory space into smaller group is called block, or you can also call it as page frames. Okay, this page frames or blocks means the same. The division of memory space into smaller size, smaller units. So total size available is 4K, that is divided into 4 blocks. So each block will have, okay, 1K words. 1K means 1024. So each block, and here the block and page size should be similar. Okay, as the page, each page has 1K words, 1024 words. So memory blocks also need to have the same size. Okay, here the pages are, each page has 1024 words, and each block here in main memory has 1024 words. So whenever a page is referenced by the CPU, okay, when a virtual address is given, here this is virtual addresses used to refer to this pages. So when a virtual address is given by the CPU, a page is located, right? Main memory is referred to identify that page. If it is there, that is executed. If that page is not available in main memory, it has to be transferred from auxiliary memory to main memory. So the first thing is the virtual address need to be converted to physical address. The address mapping need to be done. So here for address mapping, the virtual address, okay, here we have the virtual address that is placed by the CPU. How many bits this has? Here 3 bits, and okay, here we have 10 bits and here 3 bits. So totally 13 bits. It is for this memory. Okay, this address space that has 13 bits, that need 13 bits to refer to these pages. And it is divided into 2 parts. One is page number. First 3 bits are used to identify the page, and the later 10 bits, okay, are used as line number. What is line number here? these pages are numbered, right? Page 0. Okay, so as we have 8, we need 3 bits to number this. 000 is first page. 001 is the next page, page 1. 010, this is page 2. 011, 100, 101 is page 5. 110 and 111. Okay, this way the pages in the address space are numbered. And in main memory, blocks are numbered. As we have 4 blocks, we use 2 bits to number them. 00, the 0th block, 01, the first block, 10, the second block, and 11, the next block. Okay, and line number is each page. We know that each page will have 1024 words. Okay, the size of each page is 1K. So each page will have 1024 words. And when a page is identified, if suppose this is a page need to be referred by the CPU, okay, with the page number, using this page number, page is identified, page 0 is identified. And in this page, which particular word among this 1024 words, okay, among this 1024 words, which particular word in this page, okay, need to be referred, that need to be identified. So that is identified by the line number. Line number is the word number in each page. Okay, that is same here also. The line number is same. When a page is, if suppose, let's say this page 2 is transferred to block 1 here. Okay, and page 6 is transferred to block 2. Okay, from this, because CPU wants to execute page 2 and page 6. So this case, from auxiliary memory, it is transferred to block 1. Page 2 is transferred to block 1 and page 6 is transferred to block 2. Each, the same page is loaded here, right, in block 1. So in block, you will have 1024 words. And which particular line in this block, okay, which particular word, that need to be processed at that moment. Okay, for that need to be identified. Okay, so the line number is the same. If it is the 5th line in page 2, here also when it is transferred in this block, it is the 5th line in block. Okay, so the line number is same. In the virtual address, the last 10 bits are used as line number. Okay, it is the same for auxiliary memory or the address space and the memory space. Okay, in main memory. And here the first 3 bits, these bits are different. As we have 13 bits here, the first 3 bits are used as the page number. This is a page table. Okay, so we have the auxiliary memory with 8 pages, page 0, page 1, page 2, etc. up to page 7. Okay, and they are numbered as 00, and each page has 1024 words. Okay, and each word is called as lines. Line number is to refer to a particular word in the identified page. So to identify the page, here we have the page number. So this is the mapping table. The mapping table will have the corresponding block number. Okay, the mapping table has 2 fields. The first field is the block number. Okay, block number in main memory. So if suppose here the page number given in the virtual address is 101. So 101 is identified. Okay, so this is identified and the mapping table is checked. The block number here is 01. Means the main memory is numbered as 00. This is 01, 10, and 11. Okay, so it is 01. Means page 101 is available in the 01 block of main memory. Okay, so that is loaded in the buffer. Okay, here we have the page table buffer register, memory table buffer register. The corresponding block number is identified from the mapping table and that is stored in the memory table buffer register. This is for temporary storage. And this mapping table, the other field in the mapping table is the presence bit. Okay, the rightmost bit, 1 bit is presence bit. Okay, that is to indicate that if that particular page is present in the main memory or not. Okay, here we have 4 blocks in main memory. So we have 4 entries in the mapping table. Okay, means page 001 is stored in block 1 of here. Page 001 is page 1, right? Page 1 is stored in block 1 of main memory. So the presence bit is 1 here because it is available in main memory. And 010, page 010 is stored in 00, block 00. Okay, so here we have page 2. And then here page 101 means page 5 is stored in 01, block 01 in main memory. So here we have page 5 and page 110. Okay, that is page 6 is loaded in main memory block 10. Okay, so in this we have page 6. So this way these pages are loaded in block okay, memory blocks. Okay, so to map this pages to blocks, we have the memory mapping table. This indicates that which particular block, okay, this page is loaded into which particular block. And the presence bit says 1 if it is available in memory. So if the presence bit is 1, that particular block number is loaded in the memory table buffer register. And then that is used as the memory address, used to refer the main memory, okay, main memory word, and is stored in main memory address register. So this 01 that is taken from this mapping table as the leftmost 2 bits, and the other 10 bits are same as, okay, other 10 bits are this line number that is taken from the virtual address. Okay, as I told you, line number is same if it is in the 101 page, okay, and which is loaded in 01 block of main memory. If the fifth line is to be referred, this referred to that line, okay, and it is the same in block also, it is the fifth line. Okay, using the line number, it can be referred. Okay, so this way the virtual address, so here if you see, the virtual address has 13 bits that is converted into the main memory address or physical address of 12 bits. Okay, this has 12 bits. Now this is used to refer to a particular word in this main memory, and that content is extracted for processing and stored in memory buffer register. We have seen here the main memory content is stored in main memory buffer register. Okay, that is MBR here. The content that is accessed is stored in buffer register temporarily to be transferred to CPU. So this way, okay, using the virtual address, the memory address, memory content is referred through mapping. And here one disadvantage is we are learning about associative memory page table. The page table here, if you take this is the memory mapping page table. In this memory mapping table, how many entries are there? Only 4 entries. So the number of entries in the page table would be equal to the number of blocks in main memory. Okay, but generally when this is we need a separate space for maintaining this page table, correct? Mapping table. We have the auxiliary memory that is divided into pages and main memory that is divided into blocks. Okay, and the virtual address space, and we have a physical memory space. And to map the virtual address into physical address, we have this mapping table. So this mapping table has to be maintained somewhere, stored somewhere. It may be in some cases it is stored in main memory, or in some cases it is stored in a separate memory unit. Okay, somehow the computers require a lot of space to store this mapping table. Okay, so those many, how many pages are there in auxiliary memory, that many entries are allocated. So such a big size is allocated for this mapping table, but not used, right? It is completely not used. Okay, this is used because there is a corresponding block in memory, and this is used. Okay, only 4 units are used here. The other part of this memory is allocated but not used. Okay, so this way the memory space is wasted. So to avoid this, we use associative memory page table. This page table is constructed with the number of words equal to the number of blocks in main memory. Okay, we have 4 blocks here. Only 4 entries are used. For that, associative memory page table is used. Okay, in this concept, the page table is constructed with the number of words that is equal to the number of blocks in main memory. In this example, main memory has 4 blocks. So here, this is the page table. Okay, this is the page mapping table. Okay, it is constructed with 4 words. Okay, associative memory is content addressable memory. The virtual address that the CPU generates is placed in the argument register. Okay, argument register has the virtual address with the first 3 bits as the page number and the last 10 bits. Okay, 10 bits as line number. And key register is used to identify the key. Okay, that need to be compared. Identify the key that need to be compared with the content of associative memory. We don't need to compare the entire content of this virtual address with the memory content. So to identify the key, okay, what is the key we used here to compare? We used the page number to identify the page and find the corresponding block in main memory. So here the key is 101, the page number. Okay, so in the key register, these bits are set to 1 and the other bits are 0. The key used is now compared with the content of this associative memory. Associative memory has 2 fields. One is the page number. Here the page number is the content of this memory. Okay, the page number and the corresponding block number in main memory. 101. Okay, so this is located 101 and the corresponding block is 01. So that is stored in the memory table buffer register. The other process is same. 01 is stored in the memory table buffer register, and then using that the main memory address, the physical address, is generated, and that is used to locate the particular word in main memory. Okay, otherwise the process is same. So when the virtual address is placed, it is compared with the page numbers. So that the page number here is the content of this associative memory. So the page number given in the virtual address is compared with this using the key register. Okay, when the key register bits are 1, those bits are selected as key, and that is compared with the content of associative memory. When a match is found, the corresponding entry, okay, that is the block number, okay, that is identified and taken in the buffer register, and line number. This block number is 01 and the line number, okay, what is given in the virtual memory address. No, the combination of these two are used as the physical address to refer to the main memory, okay, corresponding word in the main memory, and transferred to CPU. So virtual memory is the concept used to give the programmers the illusion that they have a large memory, even though the computer has a relatively small main memory. Main memory space is small, but the programmers will have a feel of using a large memory space. Whenever the particular part of a program is executed, it is smoothly transferred from the auxiliary memory to main memory. So virtual address is the address used by the programmer, and set of these virtual address forms the address space. And the address in main memory, actually the address in main memory is the physical address. The set of physical address, or it is also called as location. Set of physical address or locations are called memory space. So we have seen here the auxiliary memory. Okay, this is the address space. The address space can be as big as the auxiliary memory. Okay, so that is referred to as here address space. It is of 1024K. 20 bits are used to refer to this, each word in this address space. And the address in physical address, okay, in main memory is memory space. It's referred to as memory space here. The size here is 32K. Okay, whenever a program or data is needed for execution, it is transferred from auxiliary memory to main memory. but the address used by the CPU is the virtual address, not the physical address. Okay, so there need to be a mapping mechanism that maps the virtual address to the corresponding physical address. Okay, virtual address is the address of the auxiliary memory, but the program or data that is in auxiliary memory cannot be accessed by the CPU. So that address need to be converted to the physical address, okay, the actual address of main memory, so that the CPU can access that. Okay, so internally the conversion takes place. That is called mapping. Okay, that is done using a mapping table. Mapping table is used to convert the virtual address to the physical address. Okay, that is a location in main memory. For mapping this, okay, pages into blocks or the virtual address space to memory space, address space is divided into pages and memory space is divided into blocks or page frames. Okay, and whenever a page is needed to be executed, it is transferred to the corresponding, transferred to one of the block in main memory. Okay, so now this page need to be mapped to the corresponding block, okay, where that page is stored. So virtual address, the page is identified by the virtual address, blocks are identified by the word, and the block is identified by the physical address. So the virtual address need to be mapped to the physical address. Okay, so how this page table converts this virtual address into physical address we have seen here. The virtual address has two entries. One is page number and the line number. Line number is in every page. Every page has, every page has 1024 words. Okay, so which particular word in the selected identified page, which particular word, that also need to be identified. That is identified by the line number. Even the same page is transferred to blocks. So in block, when a block is identified, the block has 1024 words, which particular word. So line number is the same here, and page number is used to identify the page. So when a page is identified, the corresponding block, the page table or mapping table gives the corresponding block number. Okay, so that is used to generate the physical address. So that block number, okay, that is given by the mapping table is used as the used to refer to the particular block in main memory. Okay, so block number with the line number gives the address of the word in main memory. That is accessed and stored in memory buffer register and later transferred to CPU for processing. And the huge space is allocated for this page table, but it is completely not utilized. Okay, the number of words in this page table used are equal to the number of blocks in the main memory. So it is better if we can allocate only those many words. Okay, instead of allocating so many words and using few. Okay, so the remaining space is wasted here. So it is better to allocate only those many, a little size that is equal to the number of blocks in main memory. That is implemented by associative memory page table. Okay, in this, the page number, here it is content addressable memory. So it is compared, the page number given in the virtual address is compared with the page number in the associative memory. Okay, and it gives the corresponding block number in the main memory. That is, when the block number is identified, the line number is used, okay, with the block number to identify the particular word in main memory, and that is transferred. The page referenced by the CPU is not available in main memory. Okay, when the page referenced is not available, for example, here it is 101. So instead, if the page number given by the CPU is 011, okay, let's say the page number is 011. So it is identified, 011 is identified, but that page is not available in main memory. Okay, so this condition is called page fault. So page fault is the page referenced by the CPU is not in main memory. In this case, a new page should be transferred from auxiliary memory to main memory. So that can be done. But here, if suppose the main memory is full, and a page need to be brought from main memory, auxiliary memory to main memory. In that case, the memory, the page that is available in main memory, one of the page need to be replaced. Okay, that is called page replacement. Okay, page replacement is if the main memory is full, it would be necessary to remove a page from main memory, okay, memory block, to make room for a new page. One page need to be removed or replaced with a new block. So which particular block need to be replaced? We need to identify that. Okay, so the policy for choosing pages to remove is determined by replacement algorithm. The commonly used two algorithms are first in, first out and LRU. This is first in, first out, and the second one is least recently used, LRU. Okay, first in, first out is a page that is transferred first, okay, that is stored first in main memory, is removed first. Okay, that is first in, first out. We learned about stack, right? So it is a last in, first out list. Okay, the first entered data item will be stored here, and then when the next data element need to be stored, SP, stack pointer, is incremented and the second data element is stored. And when the third another element is inserted, it is incremented and the third data element. So always it is done at the top position only, insertion and deletion. Okay, when a data element need to be removed, it can be removed. The top element only can be removed. This is last in, first out list. We have already learned about this. So here it is first in, first out. Okay, to implement this, okay, replacing the first entered page with the new page, okay, that is coming from auxiliary memory. So how this can be implemented? How to identify the first entered page? For that, a first in, first out list is maintained. Okay, so first in, first out list is represented as a queue here. Okay, this is the first in, first out list, or we call it a queue. Okay, it is like people standing in a queue. The first person entered in the queue will be served first. Okay, so here this is the first data element that is inserted. So entry is in this way. So this is the first data element. Second data element is inserted. So this is the second data element. And when there is another element to be inserted, it is inserted in the third position. And deletion will not happen at this position. It will happen at the other end. Okay, so what is there at the other end? The first data element that is inserted. We call this as front position. Okay, where the insertion takes place, and rear where the deletion takes place. So deletion of elements are done at the rear position. So at this position, the first element that is available is the first inserted element. So such a list is maintained. Okay, queue is maintained. And whenever a page, we are here talking about the pages and blocks. Okay, pages in auxiliary memory and corresponding blocks in main memory. When a page is transferred to main memory, okay, the identification number is stored in the queue, okay, in a first in, first out list. Okay, so let's say this is page 1. Okay, so here it is inserted. And then when another page is transferred, that is again the identification stored in a first in, first out list. So once a condition arises when there is a page replacement needed, this queue is checked. Okay, the first in, first out list is checked to identify the page that is stored in main memory first. Okay, which is the page that is stored in main memory first? The number that is at the rear position. Okay, at the deletion point. So that corresponding page is removed. So or replaced with a new page. So this way of replacing the first entered page in the main memory with a new page, okay, from the auxiliary memory is called first in, first out. And the second way of replacement is LRU. Okay, it is least recently used. Okay, least recently used means it is not used for a long time. How is this implemented? How to identify the least recently used page? Whenever a page is inserted, let's say page 1, the main memory has We are talking about main memory, so we call it as blocks. Okay, block 1, block 2, block 3, and block 4. Okay, we have this 4 blocks in main memory, and the pages are stored here. Okay, this has page 2, and this has page 1, page 3, and page 6. Okay, are stored in these blocks. A counter is maintained. Okay, to identify the least recently used page, a counter is maintained for every page. Okay, so let's say this is counter 1 and page 2. Okay, or the block 2, the counter 2, 3, and counter 4. And after a particular interval, the counters are incremented. Okay, after a time, a particular period of time, all the counters are incremented by 1. And again, after a particular period, okay, the fixed time period is given. So after that, it gets automatically incremented. And when the CPU refers to a particular page, if suppose the CPU wants now page 3 to execute page 3. So when it refers to this page, it clears this counter. Okay, so C3 is cleared to 0. Okay, because this is referred. When the CPU refers it, it is cleared to 0. Okay, and the increment happens after a particular period. So it is incremented. When it is incremented, 1. Okay, and when a page is referred by the CPU, let's say now page 1 is referred. So this counter is cleared by the CPU. Okay, it will set this as 0. And if at the incrementing time, every counter is incremented by 1. And if suppose CPU also now refers page 2, okay, so this counter will be set to 0. Okay, and if now a page need to be replaced, okay, which is not available in main memory, need to be brought from auxiliary memory. Main memory is full. So which page to replace? The page that has the highest count. Okay, here the page that has the highest count is page 6, that is in block 4. Okay, that has the count is 4 here, whereas the count here is 0, that is recently referred. Okay, the count, if the count is 0 means it is recently referred by the CPU. This is the most recently referred, and then this is also referred recently, and this one has the count 2. Okay, this has a count 4. So this is the least recently referred page. Okay, this is replaced by the new page from the auxiliary memory. This way, the least recently used page is identified and replaced by the new page. That's about virtual memory. Okay, so with this we finish this chapter. We'll start the 5th unit in the next class. Any doubts here? If you have any doubts in this virtual memory, you can clarify. How we take presence bit. Presence bit is to indicate if the corresponding this page is available in main memory. Okay, this page table has 2 fields. One is the block number. If page number 001 is available in block, okay, available in main memory, the corresponding block number will be will present in this mapping table. Okay, this means here 11 means page 001 is available in block 11, which is block 11, this one, third block. Okay, when we number it 0001 1011. So it is, this is page 001 is page 1. So page 1 is available in block 3. And this presence bit, okay, will be set when there is a block number present. Definitely this will be 1. Okay, to indicate that the page, this page 001 is available in main memory. So if there is no entry here, the presence bit is 0. When here, when it is mapped, okay, 001 is checked, as it is available in main memory in block 11, it is set as 1. So if the presence bit is 1, that means it is available. So the corresponding block number is taken in this buffer, okay, to generate the physical address, corresponding physical address. So presence bit is set if there is if the page is available in the main memory in some block. Got it? Okay. Let me check the attendance.